Hello everyone, welcome to my talk today. I am Mohammad Abdul Halim, working as a postdoctoral fellow at the University of Toronto. Today, as a lead author and on behalf of my colleague, I'll be sharing some exciting findings on greenhouse gas fluxes from green roof substrates and how biosphere can be used to mitigate greenhouse gas fluxes from green roof substrates. Results I'll be sharing today are from these two green roofs experiment at the University of Toronto. The top one is called GREAT Lab 1. The acronym GREAT stands for Green Roof Innovation and Testing Laboratory. This one was established in 2011. And the bottom one, we call it GREAT Lab 2, was established in 2019. GREAT Lab 2 has biocide treatments. And in this talk, I'd like to also clarify that when I say greenhouse gas fluxes, I only mean CO2 and methane fluxes. All right, now let's dive into the details of greenhouse gas fluxes from green roof substrates. Green roofs uniquely combines environment, people, and the building. It is a very sustainable way to make our cities climate smart. It offers several ecosystem services. Those are otherwise lost from rapid urbanization. The carbon sequestration potential of green roofs is of recent interest, as rapid urbanization is disproportionately responsible for ecosystem carbon losses. Appropriate management of green roofs can potentially compensate for carbon loss from urbanization. So, understanding carbon fluxes from green roofs are very important. Green roofs exchange carbon fluxes with the atmosphere primarily via plants and substrates in the form of CO2 and methane. The net effect of CO2 and methane efflux and influx will determine whether or when a green roof is a sink or source of carbon. Here we are mainly interested in CO2 and methane fluxes from green roof substrates because most of the methane exchange happens at this component. It is therefore important that we understand the magnitude and direction of CO2 and methane fluxes and micrometeorological parameters and green roof substrates physiochemical parameters driving these fluxes to design green roofs that actually sinks carbon. Our knowledge from the temperate forest dictates that substrate temperature, moisture content, pH, EC, organic matter contents, and species composition are some of the key factors that might affect carbon dioxide and methane fluxes from green roof substrates. Our better understanding of the interrelationship between direction or magnitude of carbon dioxide and methane fluxes with their drivers will help us to make very design-specific decisions for green roofs. For example, it will help us to decide what plant species we should choose and what type of substrate we should choose, what should be the depth of the substrate, and whether there is a need for irrigation or not to design green roofs that actually sinks carbon. Now the question is, how much do we know about the magnitude and driver of substrate CO2 and methane fluxes from green roofs? Some previous studies looked at the carbon sequestration potentials of green roofs, and they found that green roofs has the potential to sink carbon. They, however, completely overlooked the methane component. Methane is 30 times more potent greenhouse gas than CO2. And there is only one study by Timok et al. 2019. They quantified greenhouse gas fluxes using a closed static chamber method for 3 representative green roofs. And they found that higher ecosystem respiration in a deeper roof system than in a shallower substrate. And also they observed net methane uptake in all systems. We are not aware of any study that has quantified greenhouse gas fluxes in green roof system based on replicated experiment as opposed to measurements of representative systems. In addition to that, Timok et al. Used the static chamber technique, which suffers from a number of inherent problems and tend to underestimate fluxes. So to overcome some of the limitations discussed and to deepen our understanding, we set up an experiment in GREAT Lab 1 experimental extensive green roof at the University of Toronto. The objectives are to estimate the magnitude and substrate characteristics as drivers of carbon dioxide and methane fluxes from grain roof substrates. In that experiment, we had 4 treatments and a total 32 insulated beds, and we did measurements in April, June, August of 2018. Using a dynamic closed chamber technique in replicated grain roof beds, we looked at how substrate characteristics such as species composition, substrate depth, substrate type, and irrigation were affecting carbon dioxide and methane fluxes from the grain roof substrates. We found that carbon dioxide flux from the experimental grain roof substrates ranged from 0.03 to 1.21 micromole per meter square per second, which are much lower than a typical natural ecosystem such as forest in this region. Our results thus indicate that grain roof substrates are unlikely to be an appreciable source of atmospheric carbon dioxide as a direct result of aerobic decomposition processes. Methane fluxes, on the other hand, range from minus 0.17 to plus 0.13 nanomole per meter square per second. Although we noticed some methane efflux during April measurements, we found that overall grain roof substrates are a small but detectable net methane sink. Our ANOVA results suggested that vegetation type was not a significant driver of CO2 and methane fluxes. However, the interaction of vegetation and irrigation was a significant driver of methane fluxes. Substrate type and irrigation were the significant drivers of both CO2 and methane fluxes. Substrate depth was a significant driver of CO2 fluxes, but not for methane fluxes. Although vegetation type was not a significant predictor of CO2 fluxes, sedum beds generally had a higher CO2 fluxes throughout the growing season compared to the native meadow-mixed species. Substrate depth, on the other hand, CO2 flux increased substantially with increasing substrate depth, averaging 39% higher in 15 centimeter depth treatments compared to the 10 centimeter depth treatments. And the values are 0.30 micromole versus 0.21 micromole per meter square per second. And beds with high organic matter content compared to the low organic matter FLL had significantly higher CO2 fluxes throughout the growing season. And the irrigation treatment, though phased out 1 year prior to measurements, interestingly had large and persistent effect on CO2 fluxes, with nearly a doubling in value observed in June and in August measurements. For methane fluxes, vegetation type and substrate depth were not significant drivers. Although we thought otherwise, methane consumption was higher in organic beds compared to low organic FLL beds. And methane efflux in April was most pronounced in the FLL substrates and for the irrigated beds. Irrigation acted to increase methane consumption, with the most pronounced effect we observed in August measurements. For both CO2 and methane fluxes, substrate temperature was one of the most important microclimatic driver. Now that we have looked at the results, the key takeaway, in my opinion, from Grid Lab 1 experiments for grain roofs are CO2 fluxes from the grain roof substrates are much lower than from the soils of natural ecosystem in this region. This suggests that grain roof substrates are unlikely to be an appreciable sources of atmospheric CO2. Secondly, organic materials as substrate are not as bad as we thought. They are actually better than the low organic FLL substrate in uptaking methane. Some highest measurements of methane uptake from this study are very close to those measured in the urban forests. This suggests that the green roofs could potentially be designed to act as methane sink of comparable importance to urban forest. So this brings up to the next obvious question. Can it use biochar to enhance methane oxidation from the green roof substrates because biospheres are known to reduce carbon mineralization, they are recalcitrants, and they can enhance water retention, and even more, in some systems, they can increase the methane consumption. And they can be very potential amendment to the green roof substrates to enhance methane oxidation.
So to test the hypothesis that biosphere can be a potential amendment to the green roof substrates, we set up an experiment in Grit Lab 2. We surface incorporated sugar maple biosphere at 20 ton per hectare in 12 beds and left another 12 beds as control. In all beds, we have sedum species, and using a closed dynamic chamber system, we measured CO2 and methane fluxes in August, September, and October of 2020. We also measured some substrate temperature, moisture content, pH, and EC simultaneously. So our results are really interesting. It indicates that biosphere had no effect on CO2 fluxes, but significantly improved the methane consumption compared to the control plots. In control plots, this methane consumption are similar to those values observed at Grit Lab 1. But in biosphere plots, these values are 200% higher than the control plot. The magnitude of both CO2 and methane fluxes varied with the measurement months, as can be seen from this graph, and methane consumption are higher throughout the measurement months. So in terms of the driver of the CO2 and methane fluxes, CO2 fluxes were generally driven by substrate moisture content, temperature, pH, and the interaction of EC and moisture content and pH. And for methane, the significant driver was the temperature. And biosphere seems to be driving the methane consumption pattern primarily by affecting the substrate temperature. So now that we have looked at the results, here are my final thoughts. So in summary, we could say that the observed CO2 flux from Grit Lab 1 and 2 suggest green roof substrates are unlikely to be an appreciable source of carbon dioxide. And extensive green roofs are a weak source of methane, and biosphere addition can significantly enhance the methane consumption rate, making green roofs comparable to the methane consumption rates observed from urban forests. And overall, our data supports the provision of a methane sink could be another environmental benefit of green roof system. And that's all for my talk today. Thank you very much for your attention.